After meeting together in order to deliberate and decide, the committee has resolved to grant the BBVA Foundation Frontiers of Knowledge Award in the Basic Sciences category in its 14th edition to Charles Pfefferman and Jean-François Le Gall for their fundamental contributions to mathematical analysis and probability theory. Pfefferman has introduced groundbreaking techniques to study the detailed structure of functions and the behavior of solutions of differential equations, including those arising in fluid dynamics. Le Gall made seminal contributions to the theory of stochastic processes by establishing key results about the fine properties of Brownian motion and by deriving the scaling limits of discrete random geometric objects as their sizes diverge to infinity. Together, their body of work opened new perspectives on the field and has had a great influence on a generation of mathematicians. Thank you very much.
Let me pick out one thing. So it is called time frequency analysis. So let me explain. If you look only at frequency, you are not seeing in detail what is happening as time varies. Perhaps a pianist hits middle C and then hits some other key shortly after, and you don't see that in precisely if you look only at frequencies. The information is hidden. Whereas if you look at time, then you can see that a key has been pressed and another key has been pressed, but not necessarily at which frequency. A significant development in pure and applied math, which has had applications in technology, is to try to do both at the same time, to try to analyze sound signals in such a way that you are looking, you are capturing what information you can about what is going on in the time, from the point of view of time, and also what information you can from the point of view of frequency. And if you try to do both too precisely, they get in each other's way. But that's called the uncertainty principle. But if you do it just right, then you understand enough from both so that it's a very powerful way to analyze signals. Now, a sound signal is a function of one variable, time. But for example, if you think about a video, um, in a video, let's say the intensity of a pixel, let's not worry about color, the intensity of one pixel depends on the location of the pixel and on time. And so when you look at a video, you are looking at a function of several variables, a location and time, space and time. And time frequency analysis applies also to, in fact, in various different ways to the study of images or videos or higher dimensional objects. And I didn't invent that, but my work contributed significantly to the point of view which enabled the study of that. But most of what I have done has the common theme that in order to solve the problem, you have to understand something about functions. For a couple of equations, in particular for the water wave equation and for an equation which governs the interface between, let's say, oil and water in sand, I've gotten involved with a team in Madrid at the ICIMAT, Diego Cordoba and Angel Castro and Paco Gancedo, Javi Gomez Serrano, and they got me interested in these problems. I knew something about them before, but much more. I learned much more from intensive discussions with those guys, and we actually showed that two particular interesting fluid equations lead to singularities. One is a water wave, let's say water and air, and the water makes a splash, and we understood mathematically why that happens and how it happens, and the other is strange behavior of oil and water and sand when the interface between them is geometrically a little bit complicated. Then very strange stuff happens. A few dozen, I guess. A few dozen. My personal favorites. Maybe my personal favorite is something called the duality of H1 and BMO, which actually has something or other to do with probability. One reason why I am so fond of the duality of H1 and BMO that I spoke of before is that it took me a couple of weeks from beginning to end. A couple of weeks. It was a combination of, one of the ingredients was sheer luck, definitely. On the other extreme, there are problems that I have studied for 20 years and have partly, but not entirely, solved. Those are the limits. Recently, we studied what happens to graphene if you cut it along a straight line. Another subject is control theory. So I find that perhaps I'm getting more applied as time goes on. So imagine you were so here's the motivating example. It has happened that airplanes in flight have been very severely damaged, and the pilots have learned in real time to fly maybe an airplane with one wing or an airplane with no engine or something like that, and have managed to land safely. So, all right, control theory is the mathematical theory of trying to control something, let's say an airplane. Well, imagine that your job is to control the airplane, but suddenly, because of perhaps of some catastrophe, you don't know how the airplane works, and you don't have much time to learn. What should you do? And so I'm part of a team with an engineering professor here at Princeton, Clancy Rowley, and several friends, some at the University of Texas, some at different universities, and we're trying to get started on that problem, to understand really what to do for a practical problem in which you don't know, in which you don't understand the system you're trying to control, and you don't understand how the controls work. That's very, very hard. But we're looking at much simpler versions of that problem, which are already challenging, and we've made some nice progress.
The jury has granted you this award for opening new perspectives in the field of mathematics. Which of your contribution would you say have achieved this breakthrough, and what new perspective have they opened?
I have worked a lot on Brownian motion, which describes the random motion of a particle subject to continual changes of direction. And then I have introduced several important mathematical objects closely related to the Brownian motion, in particular the Brownian snake, which was initially motivated by connections between probability theory and partial differential equations. This Brownian snake has turned out to be an important object to understand models from combinatorics, such as random trees and random graphs. In the last 15 years, I've worked a lot on the Brownian sphere, which is a model of random geometry motivated by physics. And it seems that my work in this area has motivated many other studies by different mathematicians, and in this sense has opened new perspectives of research.
Could you explain in particular your contributions to probability theory and their importance for research in fields such as physics?
Okay, so my research is concerned with probability theory, and more especially I've been interested in understanding large combinatorial objects. To understand this, you can think of Brownian motion. Brownian motion can be viewed as a kind of limit of displacement of a particle in the plane, which at each time step will move in one of the four possible directions at random. And if you look at the trajectory of this particle over a large number of steps, this will resemble Brownian motion. And in a similar way, the model of random geometry which I have introduced is motivated by the behavior of large random graphs. Okay. So many of these models have been motivated by physics. In fact, Brownian motion was first discussed by physicists. In particular, there is a famous paper of Einstein about Brownian motion. And these models of random geometry I was mentioning are motivated by the theory called quantum gravity. For the moment, the mathematical approach is limited to 2 dimensions, which is not so interesting for physicists, but one can hope that in the future, higher dimensions can be treated.
Could you tell us what has been your favorite result during your many years of research?
So perhaps my favorite result is the definition and the proof of existence and uniqueness of the model called the Brownian sphere. So to understand what the Brownian sphere is, you can imagine that you start from a large number of small triangles, which you are going to glue together in a random manner to form a surface which has, roughly speaking, the shape of a sphere, but which is very irregular. Okay? If you take really a very large number of such triangles, but you take them smaller and smaller, then the object that you get will be close to the Brownian sphere. Okay? So my contribution has been to show that this object is uniquely defined and that it is universal in the sense that you can replace triangles by squares, by pentagons, by hexagons. In some sense, you always get the same limiting object, the same Brownian sphere.
The jury has also highlighted the great influence your work has had on a generation of mathematicians. Could you tell us about how you see your legacy in the field and its impact on new generation of researchers?
I hope to have introduced mathematical objects that will remain important in the future and that will continue to motivate researchers and to produce new results. I've tried always to work on basic mathematical objects, like I think the Brownian snake or the Brownian sphere. These objects are sometimes difficult to study or to define in the case of the Brownian sphere, but in some sense they are basic, meaning that you can explain them even to a non-specialist who will understand the reason for introducing these objects. Okay. So I'm confident that my work on these subjects will have still some impact, some influence in the work of specialists of probability theory even in 50 years. This may be not modest, but this is what I think.
How would you define the importance for society of mathematics as a basic science and of supporting research in theoretical fields such as your own?
I think that mathematics is a language in which you can develop and understand science in general. There is a famous quote of the physicist Wigner who spoke about the unreasonable effectiveness of mathematics in natural sciences. And he also said that it is a miracle if mathematics are so efficient to formulate the laws of physics. Okay. And so modern physics use a lot of advanced mathematics. This is also true for other areas of science. Maybe it is a little bit less true in biology, but I'm convinced that mathematics will play a more and more important role in these areas too. Mathematics are also everywhere present in real life. To give just one example, the GPS, the Global Positioning System, is based on advanced mathematical analysis. So, independently of applications, I think it's very important to support theoretical research in mathematics, okay? Because even if some mathematics already appear to have absolutely no applications, such applications may come later, okay? And there is a very good example about that, which is the notion of Non-Euclidean geometry, which was introduced in the 19th century as a purely mathematical concept, and it turned out to be very important in the development of the theory of relativity. Okay? And for all these reasons, I think it's really fundamental to support research in mathematics.